So you should already have this diagram in your notes from last time. It's the same thing that we ended with last time. So we were looking at this double reflector problem. Remember where I have an incident beam with some intensity that comes traveling up here, and okay, I've put an incidence plane here, and it's completely arbitrary where I put this because this is just a parallel beam that's traveling up. So I could have put it here, or I could have put it here, and it would be the same. So that's not important. I just had to put it somewhere. We come up and we travel up to this reflector, right? We reflect off of this, and now we're going up in the vertical direction again. And again, we have some prescribed intensity on a target plane. And again, just like down here, it's completely arbitrary where I put this. This thing is propagating as a parallel beam, and it's going to look the same no matter where I put this. Okay, so some of these things are arbitrary. Right? This distance between them, little l, that's completely arbitrary. It doesn't matter what that is. I said this reflector I'm going to denote by u of x, right? So it's given by, okay, position x in this plane and then height u of x. And there's an arbitrary component to this too, in that, you know, this u of x is going to be defined up to a constant shift depending on where I decide to put this plane. So there's some constant shifts that are allowed in here. Hey, what else? This reflector was determined to be a distance v of y from the top. Let's see, our t hat is the direction of this reflected ray, and the distance between these two reflectors along this t hat direction is d. We're looking for our ray mapping, right? Y equals m of x. So what that's going to tell us is if we start on this plane at position x and we go boing, 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 now we're at the location y equals m of x over here. We said we could write down the total optical path length, so we did that last time. So the optical path length was this distance u of x plus this distance d of x, and then plus this distance v of y. And we said that's equal to a constant. So our optical path length was L equals U plus D plus V, right? Where, in particular, we're taking V at this value of Y. All right, that's OK? This looks familiar from last time? All right. You never know if you guys have fallen asleep by the end of class. This might look new. So let's try to characterize this a little bit. In particular, let's look at this distance a little bit more. And we're going to try to characterize it in maybe a couple different ways. One, I guess, obvious way to characterize it is that we have just this. And that's written down in front of us. Okay, but another way to characterize it would be to say this is the hypotenuse of a triangle, right? Where we have this distance from x to y as one length, and this distance between these two guys is another length. So we could also write d squared equals, okay, x minus y squared is the horizontal distance plus, okay, plus this distance squared. Okay, so let's see if we can try to characterize that a little bit. That is going to be this height minus this height. Okay, so that's u of x minus, okay, minus what's the overlap? The overlap is, okay, so we want this height minus this height. So that's really L minus V. Okay, so U minus L minus V. Okay, so with two expressions for D, one thing that I could try to do is eliminate D and see if I can come up with a relationship between U and V. So that's one obvious thing to try, because we know we need some kind of relationship between them. So let's look for relationship between U and V. Okay, so what am I going to have? I'm going to have L, if I eliminate this, L minus U minus V squared equals X minus Y squared plus U plus V minus little l squared. Okay, and then we simplify. So if I'm going to simplify, what do I have? I have L squared plus U plus V squared minus 2L U plus V is equal to X minus Y squared U plus V squared plus little l squared minus 2L U plus V. Okay, yes, and this is something that I can solve for U plus V. So I can get some kind of relationship between U plus V. Let's see. That guy doesn't matter. And what do I have? I have 2L minus little l U plus V is going to be equal to L squared minus X minus Y squared. Okay, so here's a simple relationship between U and V. Okay, it's going to be U of X plus V of Y equals L squared minus X minus Y squared over 2 L minus L. Okay, so in some sense, once I know one of these reflectors, I'm in good shape to immediately be able to write down what the other reflector is. Right? Now, okay, there's a relationship here between X and Y that's important that I need to kind of fully characterize that. But more or less, this is down to the problem of trying to characterize one of these reflectors. What else is important? I have these distances L and L in here. But those are sort of arbitrary, right? So I said, okay, little l, I can put these planes wherever I want. So little l could be absolutely anything. Big L also has some freedom to be absolutely anything, depending on whether I basically pick this. I could pick this reflector system up and move it down, or move it up, and it doesn't change anything. It's kind of the relative position of these two things that matters, but not, or I stick them in space. So really, capital L and little l are kind of arbitrary. I pick them to be something, and then I solve this problem. So I'm not worried about trying to solve for capital L and little l. They can appear in my final solution, and that's fine. I'm happy with that. So L and L are sort of arbitrary. What I do certainly need is to have a relationship between X and Y here. Right? This doesn't work for every value of Y. It works when Y is equal to M of X. So M of X is the thing that I really need. Okay, so let's see if we can figure out M of X. Now to figure out M of X, what are we doing? We're going from here. We're traveling in the t direction. And we're going to keep going until we hit that plane. And when we hit that plane is where we're going to find M of X. Okay, so what really happens if I draw this system, just a little bit of this system? Okay, this is t. Okay, here I said was y. Here I said was x. And I gave this height a name, which we might use later. And this distance was d. So what's really happening? The ray travels from the position x in the horizontal plane, and height u in this plane. So x and u of x is where it starts. It travels along the t direction for a distance d. And it travels to x u of x plus t hat times t of x. Okay, so right now, what do I care about? I care about basically the horizontal component of this. This is what I'm trying to solve for, m of x, and the height. Height I'm not worried too much about right now. So what I really want in my ray mapping is going to have the form okay, it's going to look like m of x equals x plus t1, t2 times d of x. Right, so the vector t lives in 3 dimensions, and now I'm just pulling out the first 2 components. That's what I care about. And we can try to work out what t is. We did this for the single reflector problem already, right? We know we come in at the z hat direction. We have this normal that's determined by the reflector surface, so we can work out what t hat is. So the law of reflection gave us that t hat was z hat minus 2 z dot the normal times the normal. That's not any different than the expression that we had in the single reflector problem. So we already know how to write this in terms of the gradient. This was 1 over gradient of u squared plus 1. And then we had 2ux, 2uy, and then I think it was the gradient u squared minus 1. Okay, so if I go back to the ray mapping that I want, I know what t is, right? T is now given by, basically the gradient of u rescaled. So I have that. Now what I need is some better expression for d here. So we've got to try to go back to the things that we said about d over here and see if we can pull out a cleaner expression for that. Okay, so we have this is a good starting place, I guess, for d. I'll rewrite it. So d of x was L minus u minus phi. Or in other words, L minus u plus phi. Okay, now what's u plus phi? We've got a convenient diagram to help us out here a little bit. So that's this distance from the source plane to u plus this distance from v to my target plane. So what am I going to get in here? I'm going to get this entire distance counted in here, plus some of the area, some of the distance has been counted twice, right? So the distance from here to here has been counted twice. So we need to add that back in. So really I have that u plus v is little l plus this distance h. I'm just trying to get it in other terms where we can simplify it. That's one way to read it off. So I could try to write it like this. This is little l plus h. Okay, h, let's see what h is. So maybe we need a little triangle here to try to work out what h is. Right, so this distance we know is d. This distance was x minus y, and this distance is h. Okay, so let's see what we get here. We have this distance. This direction was t, and we have a distance d. We have this distance was h, and this distance was our x minus y. Okay, this vector is minus z hat. This vector is t hat. Okay, so this is just like high school trigonometry, so we're going to try to work out h in terms of the other things that are in here. Right? We've got hypotenuse, right, times, and then we need to know this angle, right, times the cosine of this angle. So if we call that angle, say theta, h equals d cosine of theta. Okay, and what's the cosine of the angle in terms of things that I have written here? Yeah, it's a dot product, right? Okay, so this is going to be d times the cosine of the angle is just going to be what happens when I dot these two angles together, minus z hat dot t hat. Okay, and all right, z is a particularly simple vector, right? So this dot product is just going to pull out the third component of t. Okay, so this is really minus d times t3. And t3 we know, right? We know all the components of t. All right, so if I go back to my expression up here, what do I have? d of x is equal to l minus little h, which is now d times t3. And now we're in business, right? Now I can read off an expression for d in terms of things I know, right? This capital L minus little l was whatever we decided to make them when we set up the problem. T3 we know over there. So what do I have? I have that d of x is going to be L minus L over 1 minus T3. Okay, T3 is all of this. So let's see, 1 minus T3 is going to be, let's see, grad u squared plus 1 minus all of this, so 2 over grad u squared plus 1. Goes in the denominator. So I have L minus L, grad u squared plus 1, divided by 2. Okay, so it's not so bad, right? I'm just trying to use basically high school trigonometry to work out the things that I need, right? I worked out in terms of the angles what the ray mapping looks like. And then we said, okay, law of reflection. And let's just study the picture a little bit and try to pull this out of here. Okay, did I write down the right expression the first time I did it? Probably not, but you know, you play around with it a bit and you pull them out.
Are we missing a grad u squared?
Am I missing a grad u squared somewhere? Where?
I'm using the third entry of...
There's a grad u squared here. Right, so it's 1 minus all of this. So 1 minus all of this is grad u squared plus 1 minus all of this over grad u squared plus 1. Right, so grad u squared minus grad u squared, and then I have 1 minus minus 1. So I have a 2 over grad u squared plus 1. And then I flipped it. So what was the goal? The goal was to get the ray mapping. So now I know T, I know D, so I think I can write down my ray mapping now. Okay, so here's my ray mapping. This is going to be m of x equals x plus T1 and T2. So I have 2 over grad u squared plus 1 times the components of the gradient times d. So 2 grad u times this constant over here, L minus L, grad u squared plus 1 over 2. Okay, so x plus L minus L grad u. Okay, so let me just try to summarize the pieces of information that we know. All right? So if I try to summarize this, we have a ray mapping. Which we can write down explicitly in terms of the gradient of this reflector. What else do we know? What other pieces of information did we use in the single reflector problem? Conservation, yeah. So we have some sort of conservation of energy principle. Right, okay, so in shorthand, I'll write that as my ray mapping takes my input intensity and pushes it forward to produce my output intensity. Right, we could write that as an expression of the integrals over these things of little sets. So we have that. And all of this right now is written in terms of grad u, in terms of only the first reflector. But we know once we know the first reflector and once we know this ray mapping, we can get the second reflector. So we have this relationship between u and v. In particular, we have an expression for u of x plus v of y. Go stop. You believe me that we have these things? We have these things. Okay. I haven't built a reflector yet, but at least I've learned a little bit. So at this point, you're wondering maybe, where in the world did optimal transport go? We haven't really done any optimal transport. This looks like the kind of thing that we see in optimal transport, but really, is there an OT problem in here, or am I just sort of trying to take the techniques that I used that worked with optimal transport in the one reflector case and just take them as far as I can until I get stuck and give up, which hopefully is not what we're trying to do. So where's the optimal transport problem? What are the two things that we have with optimal transport? We usually have this sort of conservation condition. And then we have, and there are lots of maps that satisfy this typically. And then we have an optimality condition. We say not only this, but we have some condition that says this is what needs to be true for M to be optimal. So the real question here is, if our map is given by this, is there some sort of optimal transport problem? Is there some sort of optimal transport cost function such that the optimal mapping is going to have this form? Right? When we did quadratic cost, we said the optimal mapping has the form gradient of u. This is different. This is gradient of u rescaled a little bit, shifted. So this is the real question. If I'm going to bring in optimal transport techniques, is there a cost function, c of xy, okay, such that the optimality condition, such that the optimal transport map has the form m of x equals x plus L minus L grad u. Now, there's some good news, right? This is not the form of an optimal mapping for the quadratic cost, but the good news is that we know a little bit about how to work with non-quadratic costs, right? So quadratic cost, we had the optimal map is the gradient of a convex function. Now we had some condition, if the cost is c, that we're going to look at the c subgradient of a c convex function. And we wrote down some conditions to characterize that, right? That let us actually write this as a PDE. Okay, so let's just investigate a little bit costs of this form. Investigate. So something of the form x minus y, similar to what we've done before. All right, so if u happens to be C concave potential, then we could use it to try to characterize the optimal map. Okay, so then optimal transport map has the form, right? Okay, m of x. I'm using m here. We used t before. It's the same thing. So I'm going to use exactly the expression here that I used for my transport map c before. So this was x minus grad h inverse of grad u. Okay, so if I'm solving an optimal transport problem, the map has this form. The actual map I have has this form. So what's the game? The game is to solve for h to make these two things equal to each other, right? If I can find h that makes this true, then indeed I could view this as an optimal transport map for that cost function. So this is true, and we want m of x equals x. Conveniently, there's an x there, plus L minus L grad u of x. Okay, I think I'm probably done with this diagram. Okay, so what do we really want? What we really want is, let's try to find a function h such that grad h inverse of a value is equal to minus L minus L times that value. Okay, so what am I trying to do? I'm really just trying to invert the inverse function, right? So what's the usual way I do that? I set this equal to something, and I solve for p. So if I do that, I should have p equals minus z over L minus L. And this becomes my grad h. Okay, so if I'm going to do this with optimal transport, I need grad h to have this form. Looking at this over here, is this actually a gradient? Yeah, sure it is, right? So this is the gradient of a quadratic function. So if this is true, then h of z should be minus z squared over 2 L minus L plus a constant. Okay, so what's the sort of takeaway? The ray mapping. The ray mapping solves an OT problem with now this cost function with c of xy equals minus x minus y squared over 2 L minus L plus some constant. So if we can solve this optimal transport problem with this cost function, where does reflector number 1 come in? What does reflector number 1 have to do with the solution of this optimal transport problem? So that's important. We have a relationship between u plus v. U itself, right? In quadratic cost case, we had this equal to grad u. Now in this case, we have some other function of grad u, right? And u is going to be this C concave potential function. So the reflector surface number 1 so the reflector R1 is the C concave potential associated with this optimal transport problem. Right, so we solve this optimal transport problem however we solve it. Maybe by solving that PD that we wrote down a couple of weeks ago. We solve for u. And once we have u, we have v, because we have a relationship between them. But we can dig into that a little bit more, actually. So let's think a little bit more about R2. What did we have? We had this expression. U of x plus v of y was equal to, I don't have it written down there still, I think it was this, L plus L over 2 minus x minus y squared over 2 L minus L. Right, okay, so certainly I'm in good shape to solve for v, but But this right-hand side might look a little bit familiar. Hopefully it does. It's over here, exactly. So this right-hand side, in particular where x and y show up in here, is exactly this for a particular choice of h naught. So what I really have is u of x plus v of y is equal to my cost function. Do you remember where else we've seen that? U plus v equal to the cost function? They're duals, exactly. So in fact, u and v are a C-concave dual pair, right? So when we solve the optimal transport problem, we took our Cantor-Elbridge problem, and then we say we can write it in this dual form, and we got these dual variables, u and v, which, okay, in the quadratic cost case, they were Legendre duals, but in the non-quadratic cost, they were these C dual pairs. And these dual variables are precisely the reflectors, precisely define what the reflector should be. So u and v are indeed our C-concave duals. So actually, there's this kind of nice deep connection to optimal transport, where the goal was to find these two reflectors. And then we say, well, if we write down the right cost function, the two reflectors are exactly the dual variables for the dual problem. So these are nothing but the dual optimal transport variables.
We can only say that once we've set the dual pairs equal to the cost, right?
Once we've set the dual pairs equal to the cost, that's what lets us make that observation. Right? And now, okay, we've got maybe results about well-posedness of the reflector problem again, right? Because a priori, is there a reflector pair that lets us produce the output that we want? And maybe not. Well, now we can say, yeah, there probably is. Under some mild assumptions on the cost functions, we know about well-posedness and say, well, if you're happy to build C-concave shaped reflectors, all of a sudden, we write down the conditions that we need for this geometric optics to go through, and we say, these conditions are exactly an optimal transport problem if we restrict to C-concave reflectors, and we've got a solution. And hopefully, we've got numerics to do this. I mean, to some extent, for the general cost functions, numerics is a work in progress. It's become interesting in the last few years, I guess. People are trying to do this. Any questions on that problem?
Yeah, so did this turn out this to be an inverse problem of some sort? Because at the end of the day, we had to solve for our cost, right? And that's what lets us solve it.
Yeah, that's right. So it's certainly an inverse problem.
We didn't have the reflector specifically, right?
Yeah, so, right, we didn't have the cost either, that's right. So it's a lot of work to figure out what is the actual optimal transport problem in here. And so I posted this thesis on Canvas. Nitin Yadavu just recently, last year got his PhD in Eindhoven. And he did some work on a particular general cost function. But he has a nice table in his thesis where he kind of goes through and says, here's this nice deep connection to optimal transport. And for a lot of different setups, he says, this is the cost function. So this is the cost function for double reflector parallel beams, but he's got it for other things, for point sources, for if you're doing this with lenses, a variety of things. And all of it kind of, the problems end up being the same, just you get a different C that comes out. I can't tell if you're stretching or raising your hand. You're raising your hand, okay.
So I saw that at some point we will use the physical law of traveling the same distance.
Yeah.
Maybe I missed it. Did we use it?
We used it. So this is the constant, right? So this is the thing that we said was a constant that let us do all of this. If at the end of the day that had been a general L of x, we would have had to do probably a lot more physics to trace what was going on, and it would not have gotten such a simple relationship. Yeah.
So U and V ended up being duals and being the reflectors.
That's right.
If we generalize it to 3, 4, 5 reflectors,
So I haven't seen this done with 3, 4, 5 reflectors. I guess one thing that you have to ask, what is it you're trying to accomplish, right? So here there were 2 things I was trying to accomplish. I was trying to control the intensity, and I was trying to control the phase of the wave. Right, so they're 2 natural things to try to accomplish. I haven't seen much done beyond that, really, in these kind of settings. And there's people that want to do more complicated things with LEDs. It gets very complicated. And there's a lot, even from the modeling side, that's not really known for a lot of these problems.
Can we say something about this critical cost function? What exactly it physically means?
What does this cost function physically mean? Let's see, what does this cost function physically mean? I don't know. It feels unusual because you've got this negative sign in front of here. So like actually making these things farther apart lowers your cost. So that's counterintuitive, maybe. You can do that with costs, but we've got some of these optical problems actually trying to let x equals y makes your cost blow up. I don't have a lot of physical intuition into why that is the right cost. It kind of pops out in this neat way.
Is there a minimum to this problem?
Is there a minimum to the optimal transport problem?
To this one?
Yes, to this one there is. So this cost fits within the framework of the MTW conditions, the Ma-Trüdinger-Wang conditions. So they had these conditions where, okay, if the gradient of C is invertible, if it's sort of a non-degenerate, if its Hessian is non-degenerate and the forced derivatives kind of obey a little bit, then the problem is well posed. And this indeed fits within that framework. I mean, if you're going to, because we have these constraints, right? I in goes to I out, and these are bounded sets. The problem shouldn't become unbounded, right? Because, okay, making these things infinitely far apart lowers your cost, but that violates energy conservation, right? Where we say, we don't want these infinitely far away. We want to go from I in to I out, and these are a finite distance apart.
So you're constrained that way. So
You're sure.
You're forced the cost to go to negative.
Right, so the cost is not allowed to go to negative infinity. Other burning questions? Okay, so this was one of my other favorite applications because I got to play with it a little bit and see my code actually get used. So that's always fun. I'm going to stop with applications for now. Depending on how time goes with the semester, maybe we may or may not come back to something else. But some of you may want to also look at applications for a project and tell us more about an application of your choice. But I want to move on to talking a little bit about numerical methods. So we're going to do a few different categories of methods, probably. I'm going to start, I think, with the method that's really big in machine learning right now, entropic regularization. And that's particularly from computing Wasserstein distances, and not really for computing transport maps. And then we'll look at some different categories of transport problems. So semi-discrete, when you're going from a bunch of Dirac masses to something that's continuous. Fully discrete, Diracs to Diracs. And then the fully continuous case, where you're going continuous to continuous, and now Malgin pair starts to make sense. So there's lots of methods out there. I'm not going to talk about all of them, but I'm going to try to talk about some that I think deserve to be highlighted a little bit. And again, if you want to learn more about another method for a project, that's fine too. Right, so I'm going to, I think, start talking, or at least introduce a little bit, the idea of entropic regularization. Yeah, this is the one that the machine learning people love. So let me start by writing down the problem that we're trying to solve. I'm going to write it down in the Kantorovich formulation for now. the formulation that you want to use is going to depend on the particular problem setup that you're trying to solve. Okay, so what we're trying to solve is we're trying to find the minimum over these transport plans of cost function integrated over the transport plan. Or at a discrete level, and the discrete level is natural for a lot of things. So at a discrete level, we're trying to do this. Okay, so now we're going to minimize. We're going to add up our cost of moving from any xi to yj. So we need to sum over all the i's and all the j's of Cij, and then our transport plan that now tells us how much mass gets moved from xi to yj. And we have constraints. Right? So what are our constraints? Our constraints are that pi has to have the right marginals. Right? So if we integrated away all the y dependence, we should get the measure that we started with on x. Okay, so integrating away all the y dependence means summing over j. And this should be equal to our measure on x. Okay, and we've got to do this at all different values of I. So this is for I equals 1 to n. Similarly, if we integrate away the x dependence, we're left with our measure on y. Okay, and these better all be non-negative. All right, what kind of problem is this? It's a linear program, exactly. So we're done, right? You just throw it into your favorite optimization software and walk away. This is a big linear program. Okay, so say I have endpoints that I'm trying to move along, and you might think of them as coming from discretizing a 2 or 3-dimensional space. So n is potentially very large, or it might be data where you have millions of data points or whatever. N is very large. Now I have not only n unknowns, but I have n times m unknowns. This is potentially a very, very, very big linear program, and this is in practice going to be prohibitively large, and the exact solvers for these are going to be slow, and this is not what you want to solve in general. Okay, so I'm going to say this is a prohibitively large linear program. So to just say, solve this exactly, which, okay, in principle, sure, you can do. In practice, no, you can't do. Even just, okay, I've tried to set up these little linear programs on my computer just for fun, and if you just kind of do it naively, you run out of memory on very, very small problems. I mean, you can't, not only can you not solve the problem, you can't even write the problem down in the computer. So without doing something else clever, this is kind of a non-starter. All right, so let me try to write down abstractly a little bit more what's going on. Try to get this into a framework where we can play with it a little bit. So I'm just going to, this isn't new. Pi is basically a matrix. there's nothing complicated about that. So I'm going to say that pi belongs to R and my M, and I'm going to say R positive because I want its elements to all be non-negative. Okay, now if I look at pi as my matrix and I add up any particular row of it, or I add up any particular column of it, that's really what I'm doing here. I'm adding up adding up over the jth column or over the ith row. Okay, so for my constraints, to write them a little bit compactly, what do I have? Pi times a whole bunch of ones. Okay, this is going to be, I'm going to call this 1 sub m. So it's just m ones. Right, which is a vector. So what is this going to do? This is going to add up over all the j's. Okay, pi 1j, pi 2j, all the way down to pi nj. Okay, and what's another name for this vector? Mu, yeah. Okay, so pi times this vector of 1s is equal to mu, and then I want to do the same thing where I add up along the other dimension. So an easy way to do that is just to take pi transpose. Now I add up all these rows again, and I get mu. So this is another way of writing my constraints. Okay, so this is another way of writing my constraint set. Capital Pi is going to be the set of all transport plans, okay, that have the right size, such that pi times 1 equals mu, and pi transposed times 1 equals mu. Okay, and then I also want a little bit of shorthand for my objective function. So my objective function says I'm component-wise taking c and pi and multiplying them together and adding everything up. Okay, so I'm just going to write that this way. Okay, c and pi. So c is my cost function, it's a matrix. Pi is a matrix, same size. So by this, I just mean exactly that, that component-wise they're getting multiplied together and adding up. So this is really our problem. Our optimal transport problem is to find this. I'll call L the minimal cost. And we're trying to find the minimum overall admissible transport plans of this objective function.
We need the minimum for each entry in that product.
Well, we wouldn't be minimizing each entry, right? So this product is then getting added together.
Oh, so it's a scalar.
So it is a scalar.
Okay.
Yeah. So this is what I mean by this kind of. It's like an inner product. Okay, and again, solving directly is expensive. We need to do something else. So one problem is solving for pi, that's the transport plan. Another problem is just solving for this minimal cost. If we get the minimal cost, we've got the Wasserstein metric, right? Wasserstein metric to the p power or something. But this is hard. So one idea with hard problems in math that we do all the time is to say, let's try to regularize the problem. Let's add a term that sort of smooths out all the nastiness, and then maybe we have something that's easier to solve. And we do that all over the place. So this is an idea. Can we try to regularize? Try to regularize and create a problem that's easier to solve. Because this isn't nice. This is big. It may not be well posed, right? There's no reason to expect a unique solution in general for the transport plan. And we've seen cases like that, right, where things can go here or they could go here. When you're working in the discrete world, it's not a well-posed problem. So abstractly, this is what we might like to do. So let's try to find some kind of regularizing function. Okay, and instead compute what I'll call L epsilon. Okay, so I'm going to minimize over the same constraint set, but I'm going to minimize a regularized objective function, which is hopefully easier. So this is going to be the minimum over transport plans of that guy, and then minus some regularizing term. And we're going to hope that this is an easier problem if we choose H in a clever way. Okay, hopefully this is easier. Okay, and again, just as a quick example, we do this all the time. We might need to solve, say, something like this, which you should recognize as Berger's equation, right? And this can have shocks, it can have discontinuities. It's a hard problem. Or we might say, let's add some kind of regularizing term that makes things nicer. For example, let's try to add a little bit of viscosity and solve viscous Bergers instead for small epsilon. And this takes the discontinuities, right, and smooths them out a little bit. And now life is better. Your numerics might be easier to build. It may be easier to prove things about this. So again, we do this all the time. But we have to pick the right H.
So the original problem is sort of the same. The only problem is too large to deal with.
Yeah, so one of the big problems is it's too large to deal with. You also have issues of non-uniqueness in the solution, right? Which again, it's okay when you're computing. The Wasserstein metric is still well-defined. If there's multiple transport plans that all realize the same minimal cost, is the minimal cost you care about. But as soon as you have ill-posed problems, numerically, this can lead to problems. And again, as you say, it's huge, and we need to try to do something clever so that we can write down the problem in our computers. People get mad when you run the supercomputers out of memory. I had a buddy who did this, and there's a lot of paperwork you have to fill out afterwards. No. Okay, so let's try to find H. What are some properties that we would like to be true of this problem? Waving our hands a little bit. Well, if we can say that there is a minimum, that would be a really good start. I have created a problem that actually has a solution and hopefully has a unique solution. So if we're thinking about what properties we want, well, we'd love to have a unique minimum So what does it take for this to have a unique minimum? What kind of functions do you love to minimize? Yeah, you love to minimize convex functions. You love to minimize uniformly convex functions, right? If you've got something that's uniformly convex, now we've got a minimum. So what does this term have to do with convexity? Where does it fit in the role of, in the scheme of convex or non-convex? What kind of function is it?
The product or pi?
This product, this inner product. It's a linear function, yeah. Are linear functions convex? Yes, they're convex, but not uniformly convex, right? So I certainly have vanishing curvature. But this guy, okay, so this guy is certainly convex, but not uniformly. And that not uniformly is why we may not have a unique minimizer. We may run into the case where somewhere in our constraint set it's just flat for a while. Okay, so this guy is okay, but he's not uniformly convex. Overall, we want this thing to be uniformly convex so that we can say this has a solution. So what should be true about H? H should be concave, yeah. So we want H to be uniformly concave. Again, I'm just going to wave my hands a bit for now, but we'll try to make this more precise. When I add my regularizing term here, this has the property of smoothing solutions out, right? A second derivative likes to smooth things out. So in some sense, we probably want to smooth things out, smooth their problems. Now, what does that mean? We'll have to think about that. In some sense, we'd like H to smooth things out. Or if we're trying to minimizing all that, that means that, in some sense, maximizing H should try to make pi as smooth as possible, whatever that means. So in some sense, maximizing H, because we're minimizing something that involves minus H, should smooth pi. Did we really get the idea from the Burger's equation? That's just a toy example of where we see regularizing happening. But yeah, again, we do this all the time. So this is an idea that's been proposed and become popular in the last few years. One thing that we can define for probability measures and joint probability measures, kinds of things that we have here, is an entropy. So let's just write down this entropy and think a little bit about what its properties are. So entropy of the distribution. This type of function sort of appears naturally a lot in the literature. So why create a brand new function from scratch when there's sort of existing functions that get used a lot on probability distributions? So the entropy looks like this. It can appear in slightly different ways in the literature, and it's kind of equivalent. But I'm just going to write it down the way it's typically written down in the context of this entropic regularization. You have a pi log pi term. And then in this context, they like to subtract 1, which doesn't really matter. The pi log pi, this is the thing that you are probably used to seeing when you've seen entropy in actually different contexts, not just probability. The -1 doesn't really matter here because it just means that you're summing up all the values of pi, and that's a constant. That's equal to 1. But it kind of makes the derivatives cleaner to do it this way. And I'll just note a convention that's usually used is that h of pi is minus infinity if these things don't make sense, because obviously the log function, you can't put anything in that you want. So if any of these terms fail to be positive, we just call this minus infinity. Is this concave? We wanted something concave. You're nodding. You believe it's concave? Yeah, it's not hard to check, right? We could take derivatives. So if I take derivatives, what do I get here? I get pi divided by pi. That's a 1. And then when I take the derivative of this, I get a -1. So what's left? What's left is this log pi. Which only, okay, if we're taking the derivative with respect to pi ij, it only depends on pi ij. It doesn't depend on any of the other values of pi. So if we look at the Hessian of this, the Hessian is actually a diagonal matrix. Okay, so the Hessian of this is actually minus the diagonal of all these 1 over pi ij's. Okay, all these pi ij's are between 0 and 1. Right, so this kind of abstract matrix comparison notation, this is strictly negative. All these second derivatives are strictly negative. Okay, since pi ij is between 0 and 1. Strictly negative is good. That means, in fact, h is concave. It's uniformly concave. So h is uniformly concave. So that's great, right? Here we have, okay, our constraint set, which is a convex set. This is a bunch of linear relationships. We're minimizing something now that's uniformly convex. So there's a minimizer. This, if we regularize this way, we've got a unique minimizer. So this is good. Okay, so the regularized problem has a unique minimizer. Okay, then the second thing I mentioned is we might be interested to know what happens as we maximize h, because putting this in here, right, is going to want to make h as big as it can. What does that actually do to the, what does this regularization do to the transport plans? Right? When we had viscous burgers, we know what regularization does. It takes the shocks and it smooths them out. What does the regularization do here? So what it does, we can kind of ask, how do we maximize h? Okay, so what I'm going to do, I'm going to forget about this part of the cost function right now and just say if I'm trying to maximize h subject to distributions that live in this set, have the right marginals, what can I do? Well, I can try to write down the Kkt conditions and actually see what this looks like if you've taken optimization. So if I actually write down the Kkt conditions for this problem, okay, I have something that involves the gradient of h, which is minus log pi. I have something from my inequality constraints, right? So I'm going to let a be the term that multiplies my inequality constraint. I have something from each of my equality constraints, which are not currently written down. I sum the pi's in one direction and I get mu I, right? So I have n constraints that way. This is going to be the coefficient that multiplies that constraint. And then I have a coefficient that multiplies my other constraint that I should get my new j's popping up. So we want this. We want aij pi ij equal to 0. And our other equality constraints. Pi ij equals mu I, and sum in the other direction, and we get nu j. Right, if we can solve this, if we can write down a solution of this, because we started with a concave maximization problem, if we can write down a solution of this, it will give us our maximum. So the obvious thing to try here is to see if we can just find something where a is always 0, because that simplifies things. And if we can find something where a is always 0, then that's great. It's a solution, and we found the max. So we can try a is equal to 0. All right, so I have log pi j equals something that depends only on I, something that depends only on j. So if I kind of clean this up a little bit, what if I introduce some new variables? I'll let little bi be represented as the log of something else, and let little cj be represented as the log of something else. Then what do I have? Minus log of pi ij equals log of bi plus log cj, or log of the product of these. In other words, what do we expect for pi? Pi is separable, right? Pi depends on I and j. But really, we can separate out those conditions and write this as the product of something that depends on I and something that depends on j. So pi is separable. Okay, so we're going to write pi as, say, mi and j. Okay, it's something of that form. We'll solve this equation, and we'll solve this equation. Now we just need to use the equality constraints to decide what terms exactly go in here. So what do the equality constraints say? They say that if I add up all the j's, so if I let mi and add up all the j's, I should get mu I. And if I go the other way, add up all the i's, I should get nu j. Okay, so what should m and n be? What's that? So they should sum to 1, right? So then what is m? M is mu I, exactly, right? So if we let them be mu and nu, then, okay, they sum to 1, m is mu, sums to 1, and n is mu. So we should take pi ij equals mu I times nu j. This is the thing that's going to maximize the entropy. This maximizes entropy. So what does that transport plan really look like? Yeah, it's like a product. But in terms of the transport, what's going on in this transport plan? So if I said this was my mu, these two Diracs, and maybe this is my nu, what does this transport plan want to do? Yeah, okay. So, no, I hear what you're saying. So let me ask this. Does mass go from here to here with that transport plan? So let's say I have half amount of mass here, and half amount of mass here, and half here, and half here. How much mass goes from mu at this position to nu at this position? Well, the amount of mass that goes from I to j, right, is mu at I times nu of j. So how much mass goes from here to here? 1/4, yeah. So mass goes from here to here. How much goes from here to here? 1/4, yeah. So we got mass going there to there. We got mass going there to there. In other words, this transport plan says everything goes everywhere. It's probably not optimal, but if you ignore the cost function, right? If you ignore this c times pi and just maximize entropy, everything goes everywhere. This is what I mean by smoothing things out, right? So when we had just like a viscous term, smoothing things out means we want to make things as flat as possible. With this entropy, it wants to mix things. Everything goes everywhere. So instead of having a nice clean transport plan, it's going to try to spread out the transport plan a little bit. And okay, we're only going to get epsilon times the entropy, so it's not really going to do this. But what it is going to do is say, okay, I should have had everything just going to one place, but I'm going to smear it out a little bit and let a little bit of mass go to your neighbors as well. So it's going to be a smudged out transport plan. So this is what I mean by regularizing or smoothing out the transport plan. And that means you don't really get a transport map out of it, right? You get this smudged out transport map. So again, for an optics application, this might not be what you want to use to design a reflector. But if you're trying to compute Wasserstein metric and you get a little error on the order of epsilon because of the smudging, that might be fine if somehow we can devise an algorithm for actually solving this problem easily. So I'm out of time. I'm going to stop there. But this is the entropically regularized problem we're going to try to solve. And it turns out there's a very efficient algorithm for doing this at the expense of the transport plan smears.